I will finish the chapter 3. I think one more sections and several example. And if we have time, we can go for chapter 4, which is the torsion. So for the last part of our course, we are going to focus on chapter 3, which is axial deformation, chapter 4, the torsion, and maybe beams, okay, equilibrium, stress, deflection. It will be, it's actually chapter 5, 6, 7, but I will just mention some important parts from each chapter, 5, 6, 7, and with the examples, like typical questions. And I think that's the all the chapters we will have for preparing the final exam. Okay, so final exam will be consists of the axial deformations, the torsion, and about the beams, okay, equilibrium, stress, and deflections. And I don't think we have enough time for other part, but if we have, the last part will be about the energy methods. But the energy method is just additional resources that we can use. So instead of mechanically using the standards solutions, using mechanical principles, we can also try to take it into energy methods, which I think it's simple, but I think you need to be more familiarized with the methods. Okay, I will start by taking another example from the textbook, which is the if we have the statically indeterminate problems, but we have the thermal. Okay, we have the thermal effects. Okay? So we have some different in the temperature. Okay, for example, these questions, we have two elements. They both stress-free when they are welded together. Okay. So they are welded at section B. Okay, so, and they are also welded to the walls, okay, at A and C. You can see the figure. Okay, so we have two elements. They are all welded in between and welded at the end. Okay, well, welded at the ends. But element 1, it will be heated by some difference in the temperature, delta T. And the element 2 is just held at the reference temperature, so no changes. So we need to determine the expression for the axial force in each element. And then expression for the displacement, UB, as you can see from the picture, UB from the section B, and then it will be going forward to the right side. So we could try using the basic force method that we explored before in the previous part, and then we are going to incorporate the change of the temperature. Okay, the change of temperature, we need to know the alpha, okay, which is the coefficient of the temperature. So so it says that when the element 1 is heated, it will push element 1 to the right side, which is going to be elaborated through the UB, that is the distance that is going to be extended from element 1. But then at the point A and C, it is going to be fixed in the wall, welded in the wall. So the total elongations will be 0. Okay? Total elongation will be 0. So perhaps if we could take the sections in between, which is the section B, as our main observations, So we could take, let's say this is the 1, and this is 2, element 2. So here is the F1, here's the F2. And through our observation at the in between element 1 and 2, which is the section B, we could see that on the horizontal axis, we only have the this equilibrium. And then always remember, whenever we discuss about the axial deformation, we start with the very basic F, L, A, and E. Okay? This is, for the most part, in chapter 3, we are dealing with this. So here, we are also dealing with these elongations. So before we determine UB, we can determine first using element 1 and element 2. So you can see that the element 1 is stated from the F1 and then L1, right? And then A1 and then E1, right? But since the element 1, it has the heated, it will be having a different temperature. So we need to add expansions by the temperature. If you remember, this is taken by alpha, which is the coefficients, and the length, and also the delta T. Okay, this is very simple from physics perspective. So every time we have a change in temperature, and it is going to be change the length, then we are going to just to add the elongations with the temperature. This is the temperature effect. Okay, and then the elongation 2, nothing happened. So only adding the normal elongations, which is okay. Now the deformations, the total deformation, since A and C is a fixed point at each wall, welded to the wall, then we can write our geometry deformation. The total elongations from AC is going to be E1 plus E2, which is going to be 0, okay, because it's fixed on the both endpoints. So now, since it's 0, then E1 is actually negative E2. Or you can say E2 is negative E1, is the same thing. Which gives you all these components can be put into the equilibrium, or the deformations, the geometric deformations. So we can write F1, L1 over A1, E1, and then plus or if we write and move the elongation to the left side. So this will be plus. And the temperature will be on the right side. We have this. And now, since we have the conditions that we stated here from the equilibrium, that F1 will be equal to F2, we can solve these equations, okay, which we can, let's say the f1, f2 maybe equal just f, just to make it clear, and we can write okay, we have that. And I think we can combine these two. I think E also the same. Is that correct? Oh yeah, E is supposed to be the same. Yeah, they are the same element. So basically we can also write the E. So no need to write E here. I will factorize E to here. Okay, so suppose that here the E is equal. Okay. Let me write clearly F over E. So here will be A1, A2. This is L1, A2 plus L2, A1. Okay. So we can solve and taken as F. So this will be E. And this will be negative A1, A2, E, and then multiply with the alpha and delta T, and then over cross multiply with this. Okay, right? So we get F, okay, I suppose with some, okay, you can imagine if it has a number, you can compute and you get the F. And through that F, we could get this elongations for each part. So we can get E1 and E2. And now the questions, what is UB? You can imagine that since, suppose that this is going to be taken longer over there. Okay, so because this is going to be heated, so the element 1 should be increased, and since the total deformation is 0, element 2 should be decreased, right? So you can see that the UB actually negative E2, okay, from this logical perspective, from this side. So since element 1 heated, so we know that the E1 should be positive and E2 is negative. Then conclusions here is the UB is negative E2. So we can input all the expressions. So negative F L2 over A2E, or we can put everything here from this F here, just substitute to this one, okay? But I will just write this, okay? So you get the solutions. There are a small chapter about geometric misfit, but I think I will skip that. Okay, so we skip that misfit. Misfit means sometimes you have some deformation, but it's not fit with the design. Okay. But I think I will skip that. I will go directly to a displacement method. A displacement method, which is very similar to the basic force method. The difference is the basic force method is going to be observing the forces from each condition or each equilibrium, but displacement method we are focused on the displacement, okay, instead of force. After we get the equilibrium of the displacement, we will get the force deformation or force. Okay. I think it's better to give you some diagram and examples. So displacement method, it starts by taking the free body diagram as usual. Okay, I think free body diagram as usual, and then write the equilibrium. Okay. It can be F or moment. And then if it is having the temperature, you can write the temperature deformations. But if not, then just write the normal deformations using K. But if you skip the second part, it's actually okay, as long as we focus on the elongations, that is F, L, A, E. Okay. K is just simplifications when we write this. Okay. This is A over L. L will be this one. So this is F over P. Okay. So you can actually skip the second part. The third part is using geometry of deformations and relate all the elongations. If there is any misfit or if there is any total elongation that is supposed to be 0, we can write here. And then solving now how to solve it basically, the difference between the basic force and displacement is the solutions here. In the displacement method, we are going to solve the displacement system of displacement. So you have like a system of equations, like a linear equation, but we are going to focus on the displacement. The previous method is going to be the forces. So we have some unknown forces that we need to solve. But here we have the elongation or the displacement. Okay. So write down the displacement and then solve the element forces, which we get at the end of the results. So this is, I think, some diagram. So we usually start from here, equilibrium. If there is no temperature, you can skip this one. And then write the elongations. Okay? Write the elongations, the compatibility equations. And then write all the force deformation and the equilibrium in displacement. Okay? And we get the displacements. And after we get displacement, we get the forces. Okay? So for the previous method, we start from the force, equilibrium for force, and then we get the elongations. Okay? So we get the elongations, and now we get the force. Okay? The difference, the order is a little bit different. So let me start with the example. So start with this structure. We have a 3 elements. So element 1 is solid rod. Element 2 is a pipe surrounds element 3. So this is element 3. And the bigger one here is element 2. So element 3 is inside element 2. Okay? And it is given by, we've taken the P, the forces at the B, so forces on the right, going to the right. Okay, this is solid rod, identical to element 1. So 3 and 1 is identical, which is they are having same E, same modulus Young's. And all 3 elements, they are all attached at B. And you can ignore the thickness of the plate, this plate here. No external force at B. the three-element assembly exactly fits between the rigid walls at A and C. So it fits with A and C. So you can also write that the total elongations there, right? Use displacement method to determine the expression relates the displacement UB at node B to the axial force PB applied there. So we apply the force here, and then we try to compute the UB. Determine expressions for axial forces in the three elements in terms of the axial force dB. So what is the axial forces in three elements? Which means that we are going to take the three elements as E1, E2, and E3, okay, elongation for each part. But we need to write in terms of dB. Okay. So we can write the diagram first. Okay. So how to write the diagrams? I think better to start with the middle part, right? So let's write the plate. Okay, suppose that this is the plate at B. So we have forces here, PB. And then we have the reaction force. We say this is F1. And this will be F3 for the element 3. But we have forces surrounds the element 3. So I will draw like this. This is supposed to be the F2. Okay. Although I draw two arrows, it's supposed to be we only take it as one F2. Okay. Because this is supposed to be circular. It can be in anywhere, but I will write all the arrow as one F. Okay. Or let me write maybe F2 is distributed around circumference of the pipe. Okay. Okay, now from here we get the equilibrium. Okay. Okay, and then the second part, we start taking the elongations F, L, A, E. Okay, and we are going to write in terms of the force equaling the displacement. So we are going to write this as F is E, and this will be okay. And sometimes we write this part as K. Okay. But if you are confusing why we need to write K and then the small f, you can skip that and just writing as like this. So from each part of the elements, we can have a three equation. So F1 is and since all the elements, they are uniform elements, so I will write E. So E1 is equal E2 is equal E3. or if you want, you can write as K1 okay. And the deformations that will happen, since the endpoints are fixed to the wall, so we know that the total elongations will be 0, right? And if happens like this, I think as also similar to what we have before. So this means that element 1 will be extended, right? And element 2 and 3 will be shortened, okay? Which means the geometry of deformations, the elongation 1 will be equal to UB, and elongation 2 and 3, this will be negative. Okay. We call this also, if you remember, this is what we call the compatibility equations. Any equations that fits within the problems that can solve. Okay? And remember, what we did here is we call this problem is indeterminate problem, or indeterminate statically problem. The difference, the indeterminate and determinate, is from if we have this solution or this, the problem. If you see the forces, you see the elongations. If we do not set up this, we are not going to be able to solve these solutions. Okay? So we need to set up compatibility equations. So that is how we see. So if you have a problem, you have the equilibrium, all the things you can write, but you cannot find exactly the answer. Then you need to have another equation, okay, to solve. And to have the equation, we need to have these compatibility equations. That is the difference between the indeterminate and the regular problems in the chapter 3. So indeterminate, if you have equilibrium, you cannot solve directly unless you write the compatibility equations, which is supposed to be, sometimes it doesn't show directly in the question, so you need to assume by yourself. And sometimes some problem like this is a takeaway. If you see the endpoints like this, so it means that you can use that as your compatibility equation. Okay? Or if there's any mention some deformations specific case, then you need to assume that as your geometry of deformations, and you can use compatibility equations to solve. Okay? So it's not always like this. Okay? So it depends on the equations. Okay? But all the order how to solve is basically similar. Okay? Basically similar. You start from the equilibrium, and then you can write the elongation problem or the equations, all the equations, and then write the compatibility equations. But we need to express in terms of PB. So basically, what we are going to do next is just substitute as usual. Okay, we substitute all. For example, here we can have this. But since if we see from what we have here the negative UB. So if we want to write in terms of UB, so we are going to exchange everything here into UB, then we can write this as E1 is UB, K1 or K1 UB. This one also K2 UB but negative. This is also negative K2, K3 UB. And we can add this, or maybe if we write, if we see from this part here, basically we can write that PB is F1 minus F2 minus F3, right? So we can also write the same thing if we multiply this with negative. So let me write with the red color. So this will be positive. So this is positive, okay? And we add all of this. I hope you get my idea here. I will take all this F1 minus F2 minus F3 is equal UB K1 plus K2 plus K3, right? I already multiply with the negative. So this will becomes PB equal UB K1 plus K2 plus K3. Okay. And basically this is how we write the UB with the PB as our variables. Okay, now what we have done here, when we substitute the UB or the compatibility equations into the element force or the elongation here. This is what we call the displacement method. So we have the elongations, which is giving you from the deformation here. We substitute back here, and we are going to solve the force. Okay? We are going to solve the force. So this is what we call the displacement method. The previous method is we start from the force, we substitute the elongations. So basically, I don't want to make like the differences, but what you can do is basically you start by taking the equilibrium. You can have the equilibrium by taking the forces, and then you can have the geometry of deformation. Depends on the question or maybe the complexity of the problems. You can start with taking the geometry of deformation, put back inside the forces, and then solve the equations. Or you can have the forces and then substitute to the elongations. Okay, both will be practically similar. I mean, the process will be similar. Just the order will be different. Okay? The order will be different. So after we get this, I think the next part will be taking back the UB, taking back to here. So F1 will be E1, or here's the UB, and then A1E L1, or here will be PB over all the K1 plus K2 plus K3. And of course, K1, K2, K3 is basically the ADL, the AD over L. So yeah, I think if you write with this, maybe it's too big in the fractions. So this will be A1, or maybe just K1, okay, just to make it easier. And same thing with F2 and I don't want to write all, but you can see that this will be very similar expressions, right? Okay, so that's the displacement method. Okay. Now, another example, okay, is if we have the a different geometry of deformations. Okay. Okay, so here's the example here. So we have 3 rods. They are attached to a rigid L-shaped bracket ABD. So ABD is the middle part, if you see. And you need to determine each force in each of the 3 rods if the element 3 is cooled by 50 degrees Celsius. So it has changed in temperature. Assume the rotation of the bracket is small and all rods are force-free when the system is assembled. So we can ignore the external forces on the rods when it is assembled. So since we are going to take into the force method, because of the we need to find each force for these 3 rods. Okay? So element 1, element 2, and element 3. And basically the first thing we can do is we draw the diagram, as we can see on the right side, the picture. And of course, this is basically the diagram on the L shape in the middle. So in the point B, there are 2 reaction force from the pin. At point A, there are the rods, basically force on A. And we have the F2 on point C, and point D is having F3. So we have all the diagrams. Okay. So I think based on what we have, all the distance are, if you see the picture, are included A, B, C. So A is distance from A to B, B is from B to C, and C is from B to D. Okay. You can start with the sigma F, but I think to get rid of the reaction force at B, we can take the moment. Okay, we can take the moment. So based on, let me write here. So we can take the moment for this from the system and take it with the perspective B. So F1A minus F2B minus F3C. And then, since we have the deformations that might happen, remember we write E is F, L, A, E. And in our case here, we are going to equaling with F. So F is E, AE over L. Or the AE over L we can write as K. Okay. F1 is E1 K1, F2 E2 K2, and for F3, since we will have the difference in the temperature, we are going to have a temperature effect. So this will be taken and shortened because it was cooled down, right? It was cooled down by 50 degrees. So here's the delta. So we have this F1, F2, F3. We can write down or compute first the K1 and all the K, basically. And since all the A is the same and the difference only the L, so we can compute. This is 1070 millimeter squared. GPA defined by 1.25 meter. This will equal to, let me write the results, 56 and K2 this is 2 meter. Okay. Okay, I think we can have a break for a while. Okay, so we have now all the results for K1, K2, K3, and the effect of temperature. So basically, what we are going to do next is we're going to assume the deformations. Okay? Since we have if we see the picture, okay, the rotation is very small, but it will rotate, but very small rotations. So if you imagine, what will happen is since the element 3 is cooled by 50 degrees Celsius, so this is element 3, and cooled means in the temperature effect it will be shortened. So imagine that the L3 is going to be reduced. It's going to be very small, it's going to be smaller. So this L will be going up, and since it is rigid L shape, so it's supposed to be, the shape supposed to be the same as the original. So when this is going up, this will be going the right side. So this will be L. Maybe this will be the deformation that will happen. So this will be maybe going up a little bit, maybe going here, and L is still a rigid shape. So that will be our deformation. So based on this, we have a new length and a new assumption. So let me give you a more clear picture on that why this happened. So here is the deformation diagram. Okay. So we have some delta here, which is the shorten of the elevation tree. So this is the distance. And we have also the distance on the element 2, since it is going to be using the assumption from here, because this is shortened. Element 2 also shortened. Okay. And then element 1 is going to be extended. Okay. Element 1 is extended. Okay. So we have the delta at A, distance at A, delta at C, delta at B. Okay. And now another thing, how to use this into our equations, into our solutions, how to use so the basic or important point, what I want to say here, is we have this part, is the triangle, which is going to be very, very important. So we have the distance B, we have the distance C. So we know the ratio between this distance over this delta D and B over delta C. So that's our ratio that we can use. Okay, we can use that to solve the problem. So use that compatibility. So let me write here the compatibility equations. Then we can use compatibility equation. So we can write that this E3 is negative delta D. And we can write basically using the C over delta D equal B over delta C. Okay, so delta C is B over C delta D, or delta C is negative E2, or E2 will be negative B over C, and this will be E3 or delta D. Okay. So this is the first one, this is the second one, and we also get the triangle from here, which we can use this triangle and connect this ratio here, right? Because this is supposed to be in triangle, has the same ratio as well. So we can write C over delta D is equal A over delta A, and the delta A is E1 or negative E1 or positive because it's extended. So let me write E1 is A over C and delta D. Okay, so we can use all these three. Okay. And then we can use all these E1, E2, and E3. We can substitute to here. So let me give you some arrow. So we can use this, substitute, sub back to the force equations. So this is the displacement method. So displacement method is basically force will be equal. So the system equations, the variable will be the elongations or the displacement. So here the F1 will be A over C delta D and multiply with K1. K1 we have already computed here, but I will just write K1 first. K1 F2 is negative B over C delta D, and K2 F3, this will be K3, and E3 is this negative delta D minus the thermal effect. Okay. Okay, we get that. And basically, since we are going to determine each force, we can arrange this F1, F2, F3, because we have here the equilibrium at the beginning. This is our equilibrium. So we can try to multiply all this with the A for F1 and B for F2 and F3 is C. And I will multiply the negative with the F2 and F3 so that I will get similar structure with this. I will add all of this and make it 0. So this will be negative, become plus, okay? So become plus. This will become plus. This is become plus, plus, right? So add. So this will be A squared, B squared, and this will be, this multiply C, so adding C, right? Okay, so I think maybe not very clear in my notes. Maybe let me just rewrite this again. Sorry. Maybe I will rewrite a new one to make it easier to follow. This is negative, 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 right? Okay, so this is, let me just write all the equilibrium again. Okay. And I will rewrite this with A squared over C K1 minus, this is plus B squared over C delta D K2 so this will be minus, and plus now is going to be K3C this will be alpha, or let me write, this will be D plus CK3 alpha 3, I will expand this, okay, equal to 0. I will move this part to the right side, okay? And then I will multiply all the equation with C. So we have A squared alpha dk1 plus B squared delta K2 plus C squared K3, or let me write delta first, and K3 equal negative K3C squared alpha 3. Okay, now we have this. We can factorize the delta. So A squared K1 plus B squared K2 plus C squared K3. Okay, I think we can solve in terms of delta D. Okay, let me make it smaller, this part. Okay. I think I will erase this. Okay. So delta D is negative K3 alpha 3 L3 delta T3 C squared over plus C squared K3. Do we have the value? Oh, we have the value. Value ABC is here, okay? So A is 1.25, 1 and 2.5, so we can substitute. So substitute, let me write here, sub all values. So basically you just type in all the numbers and you get the delta, which is, I will just write the final result for the delta is 1.0648 millimeter. But it's not done yet. We need to go back to our F1 here and F2, F3. So from the delta equal the 0.064, we can write and put the delta here, and basically using delta D is 1.0648 millimeter. We get each one of the F1 will be 29.81. F2 is negative 14.907. And F3 is 20.87. Okay. So I think the important point here, so this will be tension, this will be compression, this will be tension. And if we see from the element that we have, if we could see if this is going to be make sense, I think the cooling element at the element 3, it will put the 1 and 3 into tensions. Okay? So you can see 1 is going to be tensions going to the right side, and tension on 3 will be shortened because of the cooling effect. And then the cooling effect will make the element 2 will be compressed. Okay, and I think if you see the signs, it will be really clear. Okay. Okay. I think one more example, and I think that will be the last part. Okay. So within this part, I think the important one is this, okay, the deformations. Okay. So right here, this is important. Okay. This is important. Assuming how these deformations could be the key to solve this problem. So whenever you see any geometrical shape that is related to triangle, it means that you are forcing to use that ratio of the triangle. Okay? Every time you see any problem in our mechanics of materials, because we are considering geometric shape as one aspect that is really important. So whenever you see any triangle that is going to be in your problem text, it means that you need that ratio, especially in this problem, because every time you have an indeterminate statically axial deformation, which means all the information is not enough. So you need to assume another equations that going to be set up, and it's based on the deformations. It could be the total elongation can be 0 because of the wall. It could be deformations like this, or I will show you in the next part. Or if we have any maybe not fit situations, okay? Maybe the distance is too short. Okay? Let me give you this example. Okay. So a step rod is made up of, let me put here, okay. Step rod is made up of 3 uniform elements. Okay, so it's basically similar problem. So we have 3 elements directly, 1, 2, 3. The rod was intended to exactly fit between rigid walls with the end of all the elements. It's going to be attached to the wall, okay, at A and B. However, okay, member 2, this element 2, was manufactured delta 2. So suppose that that's the distance. It's too short. The delta 2 is too short. So first, the entire rod is stretched so that its end can be welded to the wall. Okay. So this is fit with the wall, but this member 2 is delta 2 too short. And member 3 is heated. So this is some temperature here, which will affect the length. So it's heated by amount of delta T3. So which means this is going to be extended by the temperature effect. And then the question is determine expression for the displacement UB and UC from the nodes B and C as indicated in this figure from the intended original location of the nodes, and determine expressions for the internal forces in the 3 elements. So internal forces in element 1, element 2, and element 3. So let's start one by one. And this problem, because it's, I think the key of the problem is the member 2 has not fit situation. Okay? So it's not as exactly as this L. Okay? So it's too short, a small distance delta. Okay? Which means that if we try to divide into 3 elements directly, so let's say in between of this element, let's say this element 1, 2, 3. Okay, let's say this is joint between A and wall, or the end of the elements with the walls. This is also the same, elements and walls who have the joint here. And we have also joint between these elements here. From 1, 2, and 2, 3, we have this B and C joint. Okay? Okay. So that's the first thing that we can think. And we need to let me write some of the effects, okay, that we have from the problem. We have the external force, PA, right? PA or PB, because PA and PD is the external force. So we have external force PB. So if PB is positive, okay, it's going to be, according to the direction, it will be to the right side. that will make the element 1 will be in tension, right? Because if it's positive, it's going to the right side, and element 2 and 3 in compression. Okay, if it's positive. And second, the member for element 2 too short. What's the consequences? The consequences, because the member 2 is too short, then the three element rod will have to be stretched out. So it needs to be stretched out so that it's going to be attached to the rigid walls. Okay? So as a consequences, the stretch out means that all elements will exhibit or will have a tensile force or tensile internal force because of this load. So we assume that because this element 2 is too short, we need to assume that there will be stretch out. So we need to stretch out all these three elements to make to this both ends. Okay? So we need to, so because of some small distance that is too short, we need to stretch out. Then as a consequences, because of the stretch out, all the internal forces here, they will have some tensile force. Okay? So that's the second consequence. And the third consequences from the information given is we have a heating member 3. Okay? That will be, this heating will cause the element or it to push against member to its left. Okay, so we are missing some distance in member 2, but in the member 3 we are heated up so that this element 3 is going to be expanded. So it is going to be having a tensile force internally, but in 3 we also have some additional expansion from the heat. So it's kind of complicated now, but still we can track and trace back one by one. Okay, now from these three consequences, or from these three information from the given, and we know that we can make it into this joint A, B, C, D. Now we can cut all the joint, and we can observe the diagram internally by taking all this stuffs here. Okay. So in joint A, we can have the reactions from the wall of PA and then F1 at A, and B we have internal F1, internal force F1, and then we have the external force PB, right? And then we have also F2 here. And same thing for C, we have F2, F3, and the wall reaction force PB. Okay. And then for each one of them, in between here we have this L1 for the L11, L2 and L3 for all the elements. So this F, the element 3 here is between here, so you can see from each part. Okay, and then we can observe from each joint. I think we can start by looking at the joint B and C. Okay. Because the problem is on joint A and D we have this reaction forces that we still not sure what it is. But for this two, we can try to make up the equations for the force. Okay. So first is observe B and C. Okay. So joint B, we can take the sigma F. So PB minus F1 plus F2 equals 0. And then at joint C, we get negative F2 is equal F3. Or if we write PB is F1 minus F2, and this will be F2 minus F3. Oh, this is maybe plus F3 equals 0. Okay. And of course, we know that this is statically indeterminate, right? Because we have 3 unknown internal force and then only 1 external load that we know. So 3 unknowns, but only 2 equilibrium. So this is statically indeterminate. Okay. So we need to find the compatibility equation or the geometric deformations. But first, let me start with the elongations. So elongations start with the FLAE. So F is E over L, or this is EK. And I think this is very similar to what we have from the previous part, which the F1 is K1 E1, F2 is K2 E2, and for F3 the elongation will be also added by the thermal effect. Okay. So this is K3 E3 minus so we have 3F unknown, and then another 3 unknown, and then 3E, okay, E1, E2, E3. So we have 1, 2, 3, 4, 5, 6 that we don't know, right? So we need to add another equations to solve. So to solve this, imagine that in the member 2, we are missing out some part of it, okay, because it's too short, right? So too short. Or maybe I will maybe let me draw this red color as our delta 2. Okay. So we can say the deformation. Let me write here. Geometry of deformation. Okay, this is UB, this is UC. E1 is just UB. Okay, if you see from the element 1, it goes through here, only this, right? Because here will be attached to the wall, so there is no displacement here, right? And E2, we have some sort of distance here that we need to stretch out, right? We still need to stretch out so that it's going to be attached to the walls. So we have the distance here plus another UC, displacement UC. So displacement 2 plus UC, but of course not yet, because we have UB from the left side. This is going to have some reducing distance from UB. Okay, do you get it? So you need to minus UB. Okay, because it's going to be affected from the left side. Okay? And then the last part, we have some UC, which is going to be negative, right? But we add, or let me just write E3 first, okay? Because later we are going to see that in the element 3 we have the heated part, right? But that will be, I think, the last part. So E3 will be negative UC. Okay. Now we have everything here. We can substitute to our F1 here. Okay, so let me write that F1 is E1 K1, so K1 UB. F2 is, we can rewrite this K2 and multiply with the delta 2 plus UC minus UB, right? And F3 is K3. This is negative UC, negative. Okay. Okay. Now we have this, and we have the equilibrium. Equilibrium from the first part here. This one. Okay. Or maybe not this one. Maybe this one. Okay. Let me write using different color. Okay, and we substitute all into these equations. So this will be PB equal K1 UB minus K2 distance 2 plus UC minus UB. Okay, and then F2 minus F3, K2 distance 2 plus UC minus UB minus K3 minus UC minus equals 0. Now to make it simplified, let me introduce a new symbols. I will write a new symbols which is going to be PB effective loads. This will be equal to PB plus the internal force stretched out from the delta 2, the shortened distance. And I will introduce PC. This is also effective load at C, which is going to be negative K2 distance 2 minus K3 and the effect of the heat. Okay. So these effective loads, I will use this and write into our equations. So this will be K1 plus K2 after some substitutions. I will skip some algebra process, but if you substitute, this will be what you have if you use the PB effective loads. And same thing with the second equations. This will be plus so we have this PC and PB effective loads. And then from this part, we can write UB and UC. Okay. So we can apply solutions for system of equations. If you have taken some math course using matrix, you can use like a Cramer's rule and taken as, so we have variable is this, and this. So we have two equations, UV and UC, two variables. Okay. So this will be our, you can say this is our constant, right? Our constant. Okay, it can be any number. And basically we can use either some substitution or elimination, or even maybe the Cramer's rule to get the UV and UC as our solutions. Okay, because this is not having any exact number, okay? But if it is having a number, you need to just compute with the number, okay? So using Cramer's rule, we get the UB is K2 plus K3 PB effective plus K2 PC effective over K1 K2 plus K1 K3 plus K2 K3. Same thing with UC. This is K2 PB effective. So this PB effective is just to help you out with the solutions. Okay? If you're still using the same equation and number, it will be okay, but I don't think you can simply regulate the answers and you can get the directly answer easily. And plus K1 plus K2. Okay. You can basically write this as a matrix. okay, and using the determinant from this matrix, basically. And finally, that is expressions for UB and UC, and the answer for the second questions, we are going to use this UB and UC back to our equations here. So use this UB and UC, and you get sub to F1, F2, F3, and you get the final expression for each one of them. And basically that is the answer, okay? Okay. So one thing that you can actually see from our discussion within this problem is, because we have some misfit conditions, that misfit conditions will make the loads going to be applied differently. Okay, that's why if you see why we have this, or how we could see this effective load. So usually we can just use our normal PV as usual, but because we have a shortened distance for member 2, we have some additional loads that we assume that it has tension internally. Okay? So we change all the PV plus K2 distance 2 as the PV effective. So it will be our loads that is applied, okay, in the applications, because the PV will not be only the external force, okay? Because we have some internal force that will affect this PV. This is also the same for PC, because PC and PV is in between. So when we have external force PV, it will affect the whole applied force and at B and C. And so that's why we have PC effective. We need also to apply this effect from the shortened member of element 2. It will also affect this element 3. Okay? This element 3. Okay, I think that will be the end of our lecture today. So as I mentioned, your midterm, you can take the makeup tomorrow, okay? But I think only 2 students. You can choose you want to come or not. Okay? If you don't come, it's also okay. But if you come, it will be counted as a bonus point, but of course with different percentage, not the same as the other students. So see you tomorrow if you want to take the makeup exam. Okay. But if you choose not to, and then for those students who have already passing the score, I think it's okay. Okay. So up to you.